So here we again have a massless pulley, so this is an ideal system. There is friction between the table and the block over here, but there's no friction in the pulley itself. So again, this is considered an ideal system, and we don't need to worry about having some sort of torque that causes rotation in our pulley. We can consider the tension force to be the same throughout the entire rope, even as it wraps around the pulley. So there's a tension force pulling forward on the orange block and pulling backward on the blue block. And you should always see that in your picture. You should see tension forces as internal, so they'll be positive for one object and negative for the other, so that they cancel out when you look at the whole system. All right, other forces that we have in the system, we have a 3 kilogram object, so we have 30 newtons pulling down. And we do have a weight here. Now this weight doesn't actually affect directly the motion of the system. This is not going to be a part of that first step in terms of part of the net force directly, although it's going to help me calculate friction, because if there are 50 newtons pulling this orange block down, then the normal force would also be 50 newtons. And then that's what I'm going to use to calculate friction, of course, that's pulling against. So when I look at this whole system, and I just look at forces that point parallel to the rope, then I have these two objects linked, and there is 30 newtons pulling the system in the forward direction, and then there's this frictional force pulling the system in the opposite direction. Again, the 50 newtons does not show up directly in this calculation. I'm just going to use that to find friction. Friction, of course, is mu times the normal force, so that's 0.2 times 50, or 10 newtons. Okay, so we have 10 newtons here of friction. So if I want to find the net force on the system, again, I've sort of stretched that rope that's stretched around the pulley, I've stretched it out straight so that I can sort of visualize how there are 30 newtons pulling the system forward and 10 newtons pulling the system back. So I have a net force of 20 pulling the full system, so 5 kilograms plus 8 kilograms is, 5 kilograms plus 3 kilograms is 8 kilograms. And so our acceleration here would be 20 divided by 8, or 2.5 meters per second squared. All right, how would we find tension? We would look at the same situation, but just look at one of the blocks. So maybe I would choose to look at this 3 kilogram object that had the 30 newtons and the tension force working against it. For this object, the positive force would be 30. That's helping the motion. Tension is working against its motion. That determines its mass times the acceleration of the system. That gives me a tension force of 22.5 newtons. If I wanted to check my work, I could look at the forces on just the 5 kilogram object. Kind of organize my work here. These were the forces on the 3 kilogram object. So here I have tension helping the motion of this object, and I have friction, remember that was 10 newtons, working against the object's motion. So I have T minus 10 equal to this object's mass times the acceleration, and that would also give me 22.5 newtons. So again, the key thing with these problems is going to be sort of this step here, or the step where we took the rope and we stretched it out straight, and that's how we want to think about the acceleration of the system, and our direction of motion bends around the rope so that the 30 newtons is positive and the tension force is positive for the 50 kilogram object.